All right. So for those of you who are particularly observant, you notice that we've gone a very long way down our scrolling bar without a whole lot of space left. And so me and Brett are going to be adding a bit of content at this point. I'll just show you a little bit more of the functionality of raster. I'm going to show you a few ways to generate some interesting data layers and ways that you can use that stuff in some of your work if you need. And Brett might be doing some other... I don't want to say what he's going to do because he's still developing it. But anyway, yeah, so in the annotations that we'll get in the script, it would be great if you guys could also follow on through with them. But if you don't, we're going to send out the this read-on script later so you guys can still have all the data there and all of the information there and all that stuff. So where we left off last time is we had just finished doing our exploratory data analysis on some of the observer biases that we have in our data set. And we were also at a point where we had created a data frame which had all of our environmental variables as well as our lyrebird presence and absences. But there's two, I think, really interesting functions in raster, which are, yeah, I think very good for, well, at least just to know. So we had our dat layer, so let's just have another look at that. That was all of our environmental variables stuck together. And so the first layer of that, for instance, was this elevation data. I think we're going to work with the elevation data because it's just some really simply interpretable stuff. Here you have the border between New South Wales and Queensland sort of coming along this region. This is a very biodiverse region there. In fact, interestingly, for those of you who don't know, this all used to be a volcano, and this peak here used to be the center of the volcano. So this whole area, that's just kind of a fun fact. But we're going to make a layer now, which is similar to one we've made before, which is to do with translating a raster into a yes or no thing. And we're just going to transfer that by elevation, because as we said before, these lyrebirds are really heavily associated with these high altitudes. And so we're going to arbitrarily define a high altitude in this as being above 800 meters sea level. And so to do that, we just perform a logical operation on the raster. So we have our stack called dat. We have our layer called elevation. And just a logical is greater than 800. That's greater or equal. Why not? And then we just, no, we don't need to put that in brackets, but I did. We can just assign that to dat. And we'll call this layer high. So it's particularly high. And so now we've got that. There was another way we could make that, and so we'll generate again using that, which was the re-level argument. Or was it re-level? I think it was. I'll show you a way you sometimes forget what the various things are called. Reclassify, sorry. So you just do the reclassify function again, call the dat layer, and well, the layer of elevation within the dat object, and you go everything from 0 to 800 is 0. So you make that a vector. And then everything from 801 to infinity as 1. We're doing greater than or equal, so we'll make that 800. That's 799. And that'll create the exact same object. Okay. Oh, no, it won't. I'm not sure what's going on with that. Okay, well, you guys have that function earlier anyway. I've stuffed up something small in the syntax, I assume. But anyway, I don't think we've gone that you can just do it as a logical operation like that. So that's one thing I want to make. And so we have this data layer called dat high now. but there may be some ecological affiliation with how close they are to high areas. This is just another kind of really dodgy proxy for how high something is. And so we'll make a layer called prox. And prox will use a function called distance within raster. And what distance does is, we need to do one more thing first. But what distance does is it assesses the distance from every single cell on this map to a location which is not an NA value. So in this one, we're about to code all of these zeros as NAs. And then what it will do is it will measure the distance from this point here to the closest not NA value. So to give you the value for each cell as proximity to some sort of thing. And so, actually a better way to do this. We'll do that as proximity to a protected area. That makes a lot more sense. So yep, we'll do the distance as dat protected. And so you got those ones and zeros. Yeah, that should do it. That won't work just yet because the NAs in protected are coded as zeros. So we can code those as NAs. So this is one way that you just subset that. And so for every observation within dat protected, which is 0, and then call that for every object in dat protected, assign it as NA. Oh, that's wrong. Let's give it a second. It's a little bit of a costly function computationally. And so you can see there these areas which are very far away from protected areas. All of these areas are here which are protected have a value of 0 because they are within the object. And so you can see how this could be useful if you want to do proximity to town over a population of 500. You could do some sort of search for a point location for all the towns, filter them by population level. And so you could say how likely is a lyrebird to be there given how close they are to a large human settlement. And so this is one way you can query for proximity, which is sometimes an important thing to do. Okay. And now that we've done that, we can recode our protected to what we want, which is ones and zeros. I'll just put that back. Okay, so what we've done is we've created two new data layers. One is to do whether or not the location on which the lyrebird is found is high, above 800 meters, and what the distance from each location is to being in a protected area, which is saying, you know, around protected areas there might not be as much development even though they're not protected. Okay. So once again, we're going to have to do the extract function now that we have some extra data in our explanatory data set. So we'll just copy all this and put it down. That's where the rest of it is. Okay, so now we have our new data set that we're going to use for this. So once again, we'll just have a look at it, dfxt. And so what we have here is for each lyrebird observation, a measure of the elevation, the slope, the aspect, vegetation, how protected it is. And you can see here there's this very clear pattern between protected and prox. If you're protected, you're within a national park, so you have a proximity of 0, and whether or not it's high, so above 800 meters. And so from that, we're just going to start doing some of our basic modeling. The model we're going to do, as we've said many times, is a species distribution model. What a species distribution model is, it takes a whole bunch of environmental data and it will tell you where you're likely to find that species. Species, there's a whole literature on what species distributions are, models are, and how to use them, and there's dedicated packages for it. But because this isn't a modeling workshop, this is just meant to be a raster workshop, we're going to do a very simple linear model for it. But if we're going to model where these guys are, we need to have some sort of approximation for where these guys aren't. We need to have positives and negatives. And so to do that, we're going to we can never have it, because to actually prove that a creature is not in a location is exceedingly difficult. You have to go there X number of times, you have to look for scats, hair, all this sort of thing before you can definitively say this animal is in here. So what we're going to do as a proxy is we're going to take what would be where lyrebirds would be if they were randomly distributed all over the landscape. So we're going to use a function called sample random. We're just going to choose one of the data layers, so we choose slope. That's going to define the geographic extent of where we're going to sample random points. And then we need to tell it how many random points we want. And for that, if we had a truly random distribution for lyrebirds, we would see as many points as we would for lyrebirds, so the length of the lyrebird data. And we just need this little aspect of the function sp equals true, which is going to return us a points object. Otherwise, it just returns us a data frame with the variables. So we do that, and let's just have a look at what we got. First, so here's the elevation data. You guys should be familiar with that by now. I'm just going to move this to the other screen, make it easier. So that's the elevation data. This is all of our, these are the randomly generated points. So this is for all of the lyrebirds that we have in our data set. We should see them just sort of like this if there is absolutely no spatial pattern to where they're found. And now this is where our lyrebirds actually are. So even just eyeballing it, you can tell there's some sort of spatial pattern. They don't look anything like that. And so you might say, well, if you really want to get a really good estimation of what the background data would look like, it's what I did the first time, why don't you just say, I want 4 million points? The issue with that is because we don't actually have genuine absence data, what you'd be doing is saying, characterize the entire landscape, including where I know lyrebirds are, and we're going to call that our pseudo absences. So we're not going to do that. This is just kind of a conservative way to get a somewhat robust model for this, which is saying this is what lyrebirds should look like in a perfectly randomly distributed manner, if that is indeed how they're distributed. Okay, so we've already obtained all of the data we need for our lyrebirds, so now we need to obtain our data for our pseudo absences. So once again, we use extract, make it a data frame, get rid of NAs, and so, whoops. And so this we've got all these different elevations, slopes, aspect, vegetation, protected, whether or not it's high, and proximity to national parks. And even just looking at the differences between the two heads, so you can see that everything for lyrebirds has been within a national park. Most of these are not within a national park. These guys are several kilometers, and so there's a little bit difference, but obviously this is nothing. It's just showing that even looking at this small thing and the plot, we can see there is probably some sort of driver of the ecology in it. Yeah, that's nothing. It's saying do it in a single line. Okay, so now we need to, we have all this ecological data. Now we just need to code the two different data frames into whether or not they're presence or absence. So we're going to make this one column called PB, so presence or background, because it's not truly absence, it's background. So PB is 1 for the presence data, and PB is, it is presence, I don't know why I did that, and PB is 0 for the background data. And then we just do a simple R-bind to throw them together. And we should have this. Okay, so we have a lot more observations there than that. Okay, one reason why we might have a lot more observations is because we did an NA omit before. On the particular, yes, that's why. Yeah, so we had some NAs in our newly generated plots, I think. No, we rechanged that. Okay, so it's not perfectly aligned, but you can see there is a roughly similar number. I'm not really sure why that is. Yeah, okay, so it's just in those NA omits. We must have had a few sneaky NAs through there, which must have coincided with a lyrebird presence. And what we could have done is what Brett did before by running that NA omit function over all of our layers, which would have cleared every single NA we have. But we haven't, and so there would just be a few points which have landed on an NA and had made us lose this small amount of lyrebird data. Okay. And so here's the modeling aspect of it. It's a very simple GLM, just LM. We're just going to model whether or not a point is presence or background as a function of all the data. So elevation, slope, aspect, vegetation, protected, high proximity protection. Just for the Gaussian distribution. So we've done that. So for our model, eyeballing it, you can see a lot of the factors are very significant. Proximity to protected area is extremely not significant. That's not really that surprising. But also kind of surprising, being in a protected area isn't of significance. It's pretty dang low. But pretty much everything is very significant, which implies that there is some sort of ecological driver of it that we've picked up in our raster data. And just to simplify it a little bit to get rid of the rubbish, we just do a step function and just use that simplified formula which has got rid of the has got rid of proximity to protection. Just to finish off the LM, we got that. So you still have protection in there because it was, but you've ditched proximity. So having a look at the turn plots to see if it all kind of makes sense ecologically. So the most important one was elevation, which we always would know there's this kind of distinct tipping point once you get above about 600 meters, after which you are more likely to find lyrebirds or not. So that's all good, that makes sense, that matches up with ecological knowledge. Slope, yeah, this also makes sense, but it's the relationship isn't as strong, but once you get below about 20 degrees slope, you're less likely to find them, and then as you go even higher and higher, it becomes less likely. But then once again, this could be due to observer bias because people are more likely to not go rock climbing as opposed to bushwalking, so you're more likely to see people on lower slopes. Aspects, as I said before, this is a little bit rubbish because you see here at 0, it's quite low, and there is, even though it's so weak, there is a positive relationship as you go to 360, but 360 and 0 are the exact same number for aspects. So in this, we would have needed to code it as circular data. We just haven't. That's a fairly easy thing to do if you are intending on running these sort of models. You just need a couple packages. Vegetation, once again, makes sense. The denser the vegetation, the more likely you are to find them. However, there would be these kind of these correlations as you are in a protected area or a higher elevation in Queensland, which are typically protected. You're probably going to have more dense vegetation. Sorry, you're going to have more dense vegetation because nobody's clearing the area. And protected does very little, as we know. But you might consider that protected area would be particularly significant because, you imagine not being under the threat of people. These birds which have such intricate songs, maybe being near people would. Oh, yeah.
Sorry, just a quick question.
Yeah.
It might be a bit silly, by the way. What is each of the observation here? Is that 1 pixel?
No, so each of the observations is a lyrebird presence or a background data. And so the data which is, so we've characterized each of those observations of not present or present as being the raster layers below it. So here we have the elevation data. And on top of that, we also have this lyrebird data. Okay. And so for each of these lyrebird data, they're sitting on top of a raster layer, and this raster is, it has 7 layers in it. And so each of these points gets 7 observations for each of the layers that it's resting on top. So it gets an observation for elevation, slope, aspect.
That's 1 row, right?
Yes, so each observation is 1 row, and each column is one of the raster layers. And then at the end we added our own one, which was the response variable, which was whether or not it was a lyrebird observation or a background data point.
Where the background data coming from?
So we just generated over this geographic extent the same amount of observations as we had for lyrebird, but just randomly distributed.
Oh.
Yeah. Yep. Cool.
And the response is essentially binary?
Yes, it's a binary response, yeah. Oh, so we should have done binomial instead of Gaussian.
Yeah, I was wondering about
Yeah, I didn't even think about it. I just chucked Gaussian in there without thinking. Let's see what happens if we do binomial. Yeah. Sorry, everybody. Ah, yeah. We can't. Yeah.
No, I think it's
Yeah. I'll just think for a second. Yeah. How does that go down? So, that's good. Yeah, so I guess I wasn't thinking when I wrote this section, because as I said, we're not really focusing on the modeling, so I just did this as very afterthought and clearly very autopilot. So yeah, protected is more important than we gave it credit for before, and we'll see if it still holds after we do this step. But still, everything is pretty dang significant with the exception of proximity to protected area. Yep, so the only thing we dump now is proximity. Yeah, so let's have a look at these time plots. They should be fairly similar, I think. Yep, elevation is still extremely significant. Slope about the same. Aspect, once again, no sense. Okay, vegetation in the binomial model is, if I recall, I think that's a bit more steep, a bit steeper. So a little bit more influential. Protected, about the same. And high's in it, but high is just a kind of a rubbish variable anyway because it was just a binomial. Is it high? But apparently it does have something, but that's obviously masked by the fact that elevation is so important. We've already kind of got that. And then proximity, very little. Yeah, so even though protected is now one of the significant variables, it still wasn't as significant as we thought it might have been originally. So what I wanted to look at is just another way that we have to be careful with what we're looking at in the data. So I'm just going to make a variable here called cell size. It's going to produce a warning, and that's just because our data is not in latitude and longitude, which you normally want this for. So what cell size does is it goes through your raster and it tells you the size of each of your cells. You only need that if you're using long and lats, because as you're closer to the equator and further from the equator, you don't have distortion in your longs and lats as you look at it, but there is actually substantial geographic distortion. Because as you go further from the equator, even though you might still be over 1 degree by 1 degree cell, that cell is substantially smaller just because of the curvature of the Earth. And so area is useful for that. So you can say, as I look over my entire latitudinal range, what's the actual difference in the size of my cells? Because we're using a local projection, we don't really need to use it, but it's just kind of, well, we will get this warning message because it's not really that important for us. Or the variation in cell size. We just want a mean or a median. And so we just take that cell size because everything will be the same, get rid of everything which isn't NAs, and then we can just look at that. So let's see what we have. See the first 10, they're all this because they're all 90 meters by 90 meters. Every cell is 8,100 meters squared. Then we can just take that. The length of cell size over the median of cell size gives us the raster area. So raster area is now the entire area. So we have each cell, which is 8,100 meters squared, times by the number of cells we have. But how many cells? Yeah, how many cells we have tells us the entire area of our study site. So our entire study site is that big. But then if we run it over this and look at the actual area of protected areas in it, we have 30% coverage of protected areas within this particular geographic region, which is kind of unrealistic. If we were doing this study properly, we'd go over a much larger area and see, how do they, these areas of high elevation, which aren't protected and these sort of things, and seeing the influence of that. And so that might be one reason why protection isn't as significant as it could be. It might actually be an extremely significant variable, but we just haven't accounted for it in this model. And so one function I didn't mention, just this G area, that just calculates the area of a polygon object. That's from RGeos. Very simple function there. Yeah. And so just kind of to visualize it, I don't know why that's always so distorted whenever I do this plot, but you can see that the vast majority, well, such a large extent of our study region is found within protected areas. So that might be one reason why it's not as significant as we would expect otherwise. Okay, so now that we have this model, which is binomial now and much better, we can predict to our raster and try to identify where lyrebirds are present. As I said, this isn't a modeling workshop. There's much better models to do this using machine learning and with machine learning models and having cross-validation, that sort of stuff, so you can actually have good predictions of where they're going to be. And those models, when I've done them, typically have a much sharper delineation when it comes to altitudes. But if we're just going to look at it as a prediction using our current simple model, we've got this predicted presence. All right, it's binomial now. Sorry, I was used to this being between 0 and 1. Yeah, where you have these areas here, extraordinarily unlikely to find them, and these areas in green, more likely to find them, just derived from the linear model. We can plot that at an arbitrary threshold, so it's zeros and ones, so 0 is probably above 0, so being more likely. This is the areas where we kind of are more likely to find a lyrebird than not, but if you're doing some sort of management thing and you needed to say, we need to be pretty confident there are lyrebirds there before we protect it, you can up that to 80%, and you'll get a much more stringent classification of what constitutes lyrebird habitat. Yeah. And obviously you can up that to whatever figure you want to make it as stringent or not. And so that's a very kind of quick and dirty species distribution model, really. And yes, now Brett will come and share some of his stuff. Cool. Thank you for that.
More of a raster question than a model question. Where and when do you use a brick versus a stack?
So a brick.
What are the pros and cons?
Yeah. Okay. So I don't know too much about the pros and cons, but the definition between them is a stack has to have all of the same resolutions, has to have all of the same extents. And I think a brick needs to have all of the same extents, but you can have different resolutions within them. Yeah. And so in that, for me, even though there may be advantages to a brick, I've read once before that bricks are a little bit faster computationally. I've never had such a large raster data set that I really needed to ensure that I got it as fast as possible. I was always doing fairly small stuff when I actually got to that point. But it could be that you can keep your data sets in their native resolutions. You don't have to worry about getting everything to the exact same resolution. But with Project Raster, you can do it pretty easily. And yeah, that's what I can see as the only advantage or disadvantage. I guess, yeah, were there any other general questions before we go on? Or? No? All right. Do you want this, Brett?
No, I'll just speak through. No, speak through that. So I just got asked a question earlier on that I thought I might just show people because it's kind of quite handy. So one of the issues, I guess if there's an issue with R and geographical data is that it doesn't handle large data sets, like really large data sets. So say if so I do a lot of sort of time series analysis on vegetation using satellite data. So there'll be maybe 200 images and each of them will be 500 megabytes. So, dealing with something like that in R has its limitations compared to something like, say, MATLAB, which can deal with it a lot more efficiently. But there is one really good trick that I've been taught for how to speed things up with like stacks of raster images. So I just thought I'd show everyone quickly because it's handy and it saves a lot of time. So I'll just use the same file called dat, and we'll just pretend that it is a so I'll use this layer called dat, which has 7 layers in it, and we'll just assume that each one of those layers is a different image of something. So what the idea is that if you remove all the geographical data that's associated with a raster and you turn it into a matrix, you can so each layer is a column in the matrix, and then you can just compute along the columns, and then at the end, once you've finished your computations, then you can turn it back into a raster layer, and it speeds it up so much. So the way you start is I usually just call a variable something like rbase, and this is the layer that's going to have all the data associated. Am I just plotting? Okay, so rbase. So this is what's going to have all of your geographical data, so your CRS, your resolution, your extent, all that stuff. So it's just, if you type in that, CRS raster equals that, and run that. Now if we run rbase, it is simply the data set without any actual values attached to it. So it's just telling you all the auxiliary data about that data. Then we'll go through and, so I'm just going to call this TS raster, so time series raster. Then as matrix, that. So that's going to turn it into a matrix where each of those rasters is a column. So if we look at the head of that, okay, so we can see now, we can sort of clearly see elevation, all the values are going straight down. You know, for each one, all the values are going straight down. So then it's just a matter of applying, using the apply. So say if we want to work out the maximum value, we can just go apply. So we want to know, okay, so say these are vegetation data sets. I use vegetation because I know examples. Say if these are each of these are vegetation from a successive year. We want to know what the maximum amount of vegetation is in each one of those cells. We could simply go use apply and 1, so to go across. And if we do max, there are NA values in there, so NA remove. So then that will go through each of the columns, you know, through the rows, and it'll give us the maximum value.
Also use the col sums function from raster.
Okay, yep. So yeah, like us, yeah. So you could use something like col sums. The thing with apply is you can, as you know, you can put functions into apply. So you can do whatever you want, which is where suddenly apply will become quite handy. So then we've got, so if we just type out m rust, okay, so that's just given us a vector. So we want to turn now that vector back into a raster so that we can actually see what's going on. Well, so that we can see what's going on geographically. And then we use something called set values. And so we call on that rbase again, so it'll get all the geographical data from rbase and apply it to mrust. And then we can plot it, and it'll plot out now like a geographical data set. Okay, so it looks crazy. There actually is nothing there, but I hope. Okay. You're right there. Yeah, that's it. So I hope that was helpful. I just completely quit RStudio. No, I don't think so. No, that was it. That was it. But did I completely quit it then?
I go back to the left, it should said if you want to save it.
No, that's what I thought.
It's normally a Windows.
Yes, please. I'm going to step away from it. Hopefully that was one helpful thing I found. That has saved me a lot of time. Oh, okay, here we go. Okay, we're back. Magic. Yeah, so just being able to, create your own functions that you can then put in place in there. You can do all sorts of things then. Because it's just working across, and instead of having to every time deal with all that geographical data, they can just work in numbers. It's a lot quicker. So yeah. Are there any sort of general questions or comments?